Okay, so Mr. Alfred Wegener postulated that all of the continents fit together like a giant jigsaw puzzle into a supercontinent over millions of years ago, and he called it Pangea. And ever since, those continents have been sort of separating or drifting apart from one another. This seemed like a pretty crazy theory at the time, but nevertheless, Alfred went out to prove it, and he amassed a substantial body of evidence, right? Fossil evidence along the coastlines where these continents fit together, rock evidence, glacial evidence in strange places, coal deposits in strange places. Reassembling the puzzle pieces perhaps would reveal a continuation and a similarity of geologic features such as continuous mountain chains. It was a pretty amazing collection of evidence. Yet, I think scientists were skeptical, right? In fact, some of them sort of just made fun of him a little bit, and they poked fun at him, and they called it continental drift. That was sort of like a diss on a geologic diss on Alfred, because it seemed as though that these continents, according to Alfred, just floated across the ocean. Um, Alfred was never able to explain how this happened. He could not identify the mechanism. And unfortunately, he died before we could. Geologists in the 50s and 60s started to develop uh, an understanding as to how these continents could sort of just pick up and move. And part of that understanding came about from our study of earthquakes. We were concerned about where these were happening and why they were happening and how we could perhaps better protect ourselves from earthquakes. And initially, we thought these earthquakes were just scattered randomly across the planet. However, after we started to look at the data and started to map out where these earthquakes were happening, they noticed that they weren't random. Rather, they were found in very precise geographic locations. So here's a map of the last 10 years of planet Earth showing 15,000 earthquakes. And what you notice is that they aren't just random, but they are found in sort of these really precise locations. For example, circumnavigating the Pacific Ocean. What's interesting is that corresponding to those earthquakes around the Pacific Ocean are a slew of volcanic activity, and they tend to coincide. And of course, we refer to this Pacific Ocean and these volcanoes that circumnavigate the Pacific as the Ring of Fire. We find a lot of earthquake activity running north and south in the Atlantic Ocean. We find some going on in the Himalayas. So there must be a rhyme and reason to this. And what geologists came to the conclusion is that, in fact, the Earth is much like an egg. That outer shell of the egg, very thin shell, is what they call the lithosphere. And that shell is fragmented into 12 to 16 major lithospheric plates. Now, those plates move in relation to each other. Sometimes they slam into each other. Sometimes they separate. Sometimes they grind right past each other. And it's at those boundaries where the magic happens. Lithospheric plate boundaries is where we find most volcanic and earthquake activity. And so here's a map of those major lithospheric plates, the Pacific being the largest. And what you see at the boundaries are arrows, and the arrows are indicating direction of movement. Sometimes you see these arrows separating. Sometimes you see them colliding. Sometimes you see them actually just moving right past each other. And it's these boundaries where that magic is happening, where the earthquake and the volcanoes take place. And what's interesting is we also find some really interesting geologic features and formations that are synonymous with various types of boundaries. And so we're going to get to know those patterns on planet Earth. One thing that was also learned is that the crust itself is not uniform. We have oceanic crust, the crust below the ocean, and continental crust, the crust that's on the land. And they tend to be very different. They're comprised of or composed of different types of rocks. Underneath the ocean, the oceanic crust is extrusive igneous basalt. Basalt is rich in iron. It's considered mafic. Now, being rich in iron makes it more dense. So that's going to result in some interesting interactions when these crustal types collide with each other. The less dense continental crust is felsic. It's rich in feldspars and aluminum, making it low in density. It comes from granite. So when you have an oceanic crust and it collides with a less dense continental, the more dense oceanic will get pushed down below the less dense continental. It's called a subduction zone. And we're going to learn more about these features in a moment. But how does this whole thing work? Like, what is driving it? Why are these plates moving about? Sure, they're fragmented, but how come they're always on the move? It has to do with Earth's internal heat engine. And it has to do with a transfer of heat energy through the process of convection. And we know this process very well. You put a pot of water on the stove, and what happens is the heated liquid warms, and the molecules in that water expand. That's what happens when you heat something. That expansion causes the water to become less dense, and less dense water rises to the surface. So warm water is rising from the heat source down below, and as that warm water reaches the surface, it cools. Those molecules compress, and then the water becomes more dense and it sinks. And this sets up convection cells or convection currents. And when you have two convection cells next to each other, notice the arrows, they separate. Well, what caused Pangea to separate? It's the same process. If you put two wooden blocks at the surface of the water, notice these cells and the arrows move apart. They are pulling these wooden blocks away from each other. This is the exact setting. This is the exact situation that's going on below our feet in what we call the asthenosphere. It's an upper portion of the mantle. That's sort of like a fluid, but it's not a true liquid and it's not a true solid. It behaves like a plastic. So the heat coming from the core rises to the surface and gets closer, and it actually manipulates and results in this plasticity where convection currents develop in the asthenosphere. Now the lithospheric plates sit on top of that asthenosphere, and they are going to be moved by those convection cells. So here we have oceanic crust with a boundary, two convection cells where arrows are separating, ripping apart the oceanic crust, pulling apart Europe from North America, pulling apart South America from Africa. There's other things going on here too. It's not just convection, because when these things separate, gravity also tugs the plate towards the center. So it's being ripped apart by convection, and gravity is tugging those plates towards Earth's center of mass. This sets up a self-perpetuating conveyor belt on planet Earth that keeps our lithospheric plates moving. Here's what it looks like below the Atlantic Ocean, for example. If you can envision these land masses being connected during the time of Pangea, convection cells eventually started to rip apart the plate, creating tensional forces, separating the plates, creating a zone of seafloor spreading, which would deepen and widen the Atlantic basin, creating what we call the MidAtlantic Ridge. So again, we have convection cells, the driving force, putting the lithospheric plates on the move, causing them to interact with each other. Here's another image of that. Again, the heat is generated from the inner core. Convection cells in the asthenosphere are manipulating the lithospheric plates. Here we have an area of seafloor spreading, of divergence, pulling plates apart. Notice in other areas it's causing plates to collide. Where you have oceanic crust that's more dense, it gets pushed down below, gravity tugs at it, and keeps this whole system moving. So we're going to look at the different types of boundaries that we're going to actually observe from this plate tectonic process. Plates are constantly on the move, and they interact with each other. In the case of a divergent boundary, where two plates separate, we have the oceanic crust at the seafloor spreading center. Here are the convection cells. The arrows are moving away from each other, therefore pulling apart the oceanic crust. Now, the magma, which gets converted to lava as it exits at the divergent seafloor spreading boundary, creates new rock. It actually generates a parallel set of mountain chains that we call a ridge. The MidAtlantic Ridge is actually the longest mountain chain and the tallest mountain chain on planet Earth. It's just below the ocean. It's absolutely huge. And in between, where it's separating, runs a deep rift valley, and that's the zone of separation. This is an area of intense volcanic activity, earthquakes, and mountain formation. We can actually watch this in motion. Obviously, it's not moving this quickly, probably less than a centimeter per year, but over millions and millions of years, this creates a geographic area as large as the Atlantic Ocean. Again, lava is spewing out at the seafloor spreading center, where convection cells are rising, pushing the crust away from the seafloor spreading center, creating this really interesting age symmetry on the ocean floor. This distribution of aged bedrock was noted following World War II. Scientists were asked by the Navy to map out the bottom of the ocean to facilitate submarine warfare during the war. Scientists were cool with that. They did it so long as they could use the instrumentation following the war to strengthen their understanding of plate tectonics. And they developed some pretty amazing maps from it. And they developed a lot of evidence that would contribute to plate tectonics. Because what they noticed is that the distribution of rocks on the ocean floor was paralleled to the divergent boundaries. If you guys take a look for context, here's North America, South America, Africa, and Europe. Here's the Mid-Atlantic Ridge. This is the area of seafloor spreading, divergence. And the colors represent age. So it makes sense. Red is the youngest rock. Red would be found along the Mid-Atlantic Ridge, as this is where the lava is exiting the zone of seafloor spreading, creating new rock, pushing the old rock away from the ridge. It's almost, it's creating these patterns, this symmetrical pattern on both sides, as if you were to put a mirror at the ridge. This conveyor belt is separating, creating new rock at the ridge, pushing the older rock towards the continents. So it gets older and older as we move towards South America. It gets older and older as we move towards Africa. More evidence to lend credence to the idea of plate tectonics. Now, where you have plates separating, that's going to mean somewhere else plates are colliding. We call these boundaries convergent. Plates come together, and we have three different types. And they are distinguished from each other based on the type of crust that is colliding. The first type is when an oceanic crust collides with a less dense continental crust. Again, oceanic being mafic means it's more dense. When it collides with the less dense continental, it's going to get pushed down below in a process we call subduction. This subduction forces the oceanic crust down into the mantle, where it's destroyed from intense heat and pressure, building up a lot of heat that rises to the surface. Magma rises and is ejected from volcanic activity along the continental margins. This produces volcanic arcs like the Andes or the Cascades in the Pacific Northwest. At the interface where the subduction occurs, we find some of the deepest parts of our ocean, known as oceanic trenches. In some cases, they can exceed 11 kilometers in depth. That's ocean continental. Well, sometimes you get ocean-ocean, oceanic crust colliding with other oceanic crust. The older oceanic crust is typically more dense because it's cooled for a longer time period, and so that gets forced down below a less dense oceanic crust where they collide. Again, subduction results in the destruction of the crust, which forces magma to the surface, and instead of producing volcanoes on a continental margin, it produces a volcanic island arc in oceanic crust. The Aleutian Islands off the southwest coast of Alaska are a good example. The Japanese islands are also volcanic arcs produced from subduction. The last type of convergent boundary are when we have two continental crusts colliding. Sometimes we refer to this as collisional. Now, these continental crusts have roughly equivalent densities. So when these land masses collide, no subduction happens. They slam into each other and they have nowhere to go, and they crumple up and cause mountain building. These continental collisions produce the highest mountain chains on planet Earth above sea level, and the Himalayas are still rising just about a centimeter every single day, including Mount Everest. And this is the result of the subcontinent of India moving north and colliding and slamming into the Asian continent. Our final boundary type is what we call a transform or a lateral boundary. So these plates aren't colliding, they're not separating, rather they're just sort of grinding past each other. A very famous transform boundary is what we call the San Andreas Fault, which happens in southwest California. What we see here is the North American plate grinding to the southeast, while the Pacific plate is moving to the northwest. Now you can imagine there's a lot of stress and resistance that builds up along this fault line. And when the stress exceeds the resistance, it can release an enormous amount of energy in the form of seismic waves through Earth's crust, which generates quite a bit of earthquake activity that can be highly destructive. We can actually observe the San Andreas Fault from the sky, and we can see here the North American plate, which is moving to the southeast, grinding past the Pacific plate headed in a northwest direction. All right, well, that was a lot, so we're going to stop there for today, and we'll continue to look at these in Google Earth and other maps tomorrow. Have a good one, guys.